The Cold War necessitated the ultimate paradox of survival, creating an impregnable sanctuary for national leadership while simultaneously maintaining the capability to launch an immediate, devastating retaliatory strike. This dual mandate gave birth to the most ambitious and ultimately impossible subterranean construction project ever conceived, the Deep Underground Command Post, DUCP, often referenced under the conceptual banner of Project Zeus. This facility was not merely a bunker. It was a self-contained, subterranean city designed to house thousands of essential government and military personnel, ensuring the continuity of government for months after a nuclear exchange. Its defining feature, however, was the integration of vertical intercontinental ballistic missile, ICBM, silos directly into the hardened complex, transforming the sanctuary into a final, lethal military base. Before we delve into the catastrophic failure of this colossal project, please take a moment to hit the like button and subscribe to Never Built. We uncover the lost future that the world canceled. We promise you this. Stick with us until the final segment, and you will learn the one specific, chilling flaw in the missile launch design that proved the entire bunker would have been guaranteed to instantly implode upon launching its own retaliatory strike. Here is why this ultimate symbol of Cold War defense was abandoned. The first, overwhelming obstacle was the excavation impossibility. The site required boring massive, multi-level chambers thousands of feet deep into solid, stable granite, a task so vast it demanded a new generation of tunneling technology that did not yet exist. The second, inescapable hurdle was shock wave catastrophe. The bunker had to withstand the colossal seismic shock of a near-direct multi-megaton nuclear hit, requiring an unprecedented, flexible suspension system to prevent the entire underground structure from violently shattering. Finally, the project was fatally vulnerable due to launch port integrity. The necessity of creating access ports for missile launch fundamentally compromised the hardening of the entire facility, creating a single, exploitable weakness. The core engineering challenge of Project Zeus was defined by the laws of physics governing blast wave resilience. To survive a direct or near-direct hit from a multi-megaton warhead, the command post needed to be buried at least a mile deep in stable, competent rock, such as granite or basalt. This depth was required to allow the surrounding rock mass to absorb the immense pressure shockwave before it reached the main facility. The excavation required was staggering. It demanded boring vast, subterranean halls and shafts large enough to house hospitals, power plants, communication centers, and living quarters for thousands of people. The volume of rock to be excavated was comparable to the largest tunneling projects ever undertaken, yet had to be performed at depths never before attempted on this scale, necessitating TBMs that could withstand crushing rock pressure and extreme temperatures. The logistical challenge of removing the colossal volume of spoil or excavated rock was a mega project in itself, requiring dedicated vertical shafts and a continuous conveyor system, the operational costs of which added billions to the unbudgeted expense. The construction method involved creating a massive, hollow cavern and then building the facility itself inside this void. Crucially, the internal structure could not be rigidly attached to the rock. To survive the seismic shock of a nuclear blast, the entire underground city would have to be mounted on a gigantic shock-absorbing suspension system. This system was conceptualized as a network of hydraulic jacks, rubber mounts, and flexible suspension cables, allowing the internal structures to float relative to the external rock walls. The goal was to dampen the violent seismic acceleration from a blast, preventing the equipment and personnel inside from being instantly destroyed by G-forces. Designing a flexible suspension system capable of supporting the weight of a small city inside a confined, high-pressure environment represented an engineering paradox that was technically beyond the capabilities of the era, adding significantly to the complexity and the ultimate failure of the project. The immense cost and perpetual maintenance required for this hydraulic system were never financially reconciled. The logistical demands of maintaining life inside the DUCP were monumental. Once sealed, The bunker had to be entirely self-sufficient for an indefinite period, ranging from weeks to months. This required massive internal power generation, primarily from advanced diesel generators and stored fuel, huge stockpiles of food, medical supplies, and, most critically, a completely closed-loop life support and atmosphere regeneration system. Air quality, temperature control, and humidity needed to be meticulously managed for thousands of people living in isolation. The internal power plant had to be hardened against the massive electromagnetic pulse, EMP, generated by a nuclear blast, requiring extensive internal shielding and redundant systems, which added further weight and expense to the suspended internal structure. The waste disposal system, which had to process all sewage and refuse without venting contaminants to the surface, was a massive engineering feat on its own. The psychological strain on the personnel, confined for months in a deep, isolated environment, was another unbudgeted risk that planners struggled to quantify. The entire project required the creation of a massive, perpetual logistics chain, making the cost of operation nearly as high as the cost of initial construction. The ICBM integration was the unique and ultimately fatal flaw of Project Zeus. The idea was to eliminate the vulnerability of surface missile silos by burying the retaliatory capability directly beneath the command center. This required running massive, hardened silos and launch mechanisms up from the main facility to the surface, where they would be capped by massive, rapid-opening blast doors. This necessity created an undeniable single point of vulnerability. While the main command center might be a mile deep, the launch ports themselves were on the surface and required vast, easily locatable support infrastructure. A direct nuclear hit on the launch ports would not only destroy the missile capability, but the shockwave and debris channeling down the launch tubes would compromise the hardening of the entire complex. The designers could not guarantee the integrity of the underground city if the crucial launch ports were vaporized. Furthermore, the immense heat and backblast pressure generated by the missile launch itself created a massive internal stress on the entire suspended bunker structure, a flaw that would have guaranteed failure. The Cold War provided the strategic rationale for the project, but the fiscal reality provided the final, unanswerable veto. The total cost of Project Zeus was estimated to be so immense that it would consume a significant portion of the entire strategic defense budget for years, delaying investment in other crucial deterrents. The cost of excavating the rock, building the suspension system, installing the complex life support, and maintaining the integrated ICBM silos was astronomical. Political opposition, led by those who favored mobile, dispersed missile systems like submarines and rail-based launchers, successfully argued that placing all the nation's command and control and its retaliatory launch capability into one extremely expensive, fixed target was fundamentally unsound. The staggering financial burden combined with the unsolvable technical paradox of the launch ports proved that the ultimate command post was doomed to remain a blueprint. The project was essentially asking the budget to fund a structure designed to survive the ultimate catastrophe, a level of financial commitment that was simply impossible to sustain even for the most critical strategic asset. The second critical phase in the abandonment of Project Zeus was the realization that the geological environment itself, which was supposed to be the command post's ultimate defense, was also its most profound weakness. The plan required selecting a stable, massive block of igneous or metamorphic rock, ideally granite or basalt, far from any major fault lines. However, drilling a mile deep into the Earth's crust, even into stable granite, is not a simple matter of boring a neat hole. The process of deep excavation inherently alters the stress fields within the surrounding rock mass. Engineers encountered the challenge of rock spalling and microfracturing. The removal of massive volumes of rock at extreme depth causes the remaining rock walls to experience immense pressure differentials. This pressure relief results in the rock violently shedding layers in a process called spalling, similar to how concrete cracks under stress. This required complex and continuous rock bolting, shotcreting, and stabilization measures over every square foot of excavated tunnel and cavern, significantly driving up construction time and cost. The integrity of the massive suspension chamber, designed to house the floating city, was constantly threatened by these geological instability issues, forcing a perpetual and expensive battle against the basic physics of deep rock mechanics. The sheer volume of waste rock management became a logistical and environmental catastrophe that ballooned the project's budget. Excavating a complex of the necessary size a mile below the surface required removing millions of cubic yards of rock. This spoil had to be continuously lifted through narrow vertical shafts and transported away from the site without attracting attention or contaminating the local environment. The continuous operation of the vertical lifts and the transportation of the spoil by truck or rail required thousands of workers and immense energy expenditure, creating a logistical tail so massive it defeated the project's goal of secrecy. The environmental impact of simply disposing of this mountain of inert, excavated rock became a political and public relations nightmare, adding yet another layer of unbudgeted cost and complexity to the already staggering estimates. The integration of a life support system with a hardened structure presented a paradox of air and isolation. To survive a nuclear war, the DUCP had to be sealed completely, relying solely on recycled air and internal oxygen reserves. This required a colossal, complex atmosphere regeneration system to scrub carbon dioxide, control humidity, and filter out any potential internal or external contaminants. The system had to be fully protected against the seismic shock and EMP of a nuclear blast, yet it was comprised of sensitive, delicate components. The necessary redundancy of the life support system, requiring multiple parallel air processing units, consumed massive volumes of space within the already limited suspended structure, further adding weight to the shock-absorbing mechanism. The failure of even a single pump or valve in the life support system could jeopardize the lives of thousands of high-value personnel, creating an unacceptable level of operational risk. Furthermore, the need to maintain secure communication with surviving surface forces after a nuclear strike introduced another fatal structural compromise. The DUCP required massive, hardened antennae systems buried deep within the rock to communicate with submerged submarines and orbiting satellites. However, transmitting high-power radio signals through a mile of solid rock is immensely difficult, forcing the use of complex, low-frequency antenna arrays, often located in nearby, less protected surface facilities. This requirement created a communications vulnerability. The necessary communication shafts and external antennae links were easily locatable and represented pathways for the blast shockwave or hostile sabotage to reach the underground complex, compromising the entire concept of impregnable isolation. The trade-off between absolute hardening and necessary communication was never satisfactorily resolved. The internal logistics of command and control within the suspended environment added psychological and operational risks. The massive internal city had to be organized for rapid, clear decision-making immediately following a nuclear exchange, requiring high-speed internal transport, secured conference rooms, and fully functional military planning centers. The requirement for the entire command post to be structurally flexible, hanging on massive shock absorbers, introduced unique engineering challenges for internal stability. Sensitive targeting computers, communications gear, and delicate medical equipment would need to be meticulously secured and vibration dampened to prevent damage, even without a nuclear strike. The psychological effect of living and working in a suspended, isolated, high-pressure environment for prolonged periods was a major concern, leading to fears of command incapacitation due to stress and isolation. The entire design prioritized physical survival but risked functional paralysis, proving that the engineering was too complex for reliable operation. The third critical phase in the life of Project Zeus involved the strategic trade-offs that ultimately exposed the project as a failure of doctrine rather than engineering. The military purpose of the deep underground command post was twofold: to survive the first strike and to command a retaliatory second strike. However, the necessary integration of the massive, hardened ICBM silos into the DUCP structure presented a self-defeating contradiction that plagued military planners. The very act of incorporating the missile launch capability compromised the invulnerability of the command center. The engineers were forced to design massive, vertical launch tubes and ports extending from the command post a mile up to the surface. These tubes, while heavily reinforced, represented a critical discontinuity in the surrounding rock mass. A high-yield nuclear blast directed at the surface launch ports would send immense shock waves and debris channeling directly down these tubes. This would create a phenomenon known as the pipe cleaner effect, where the blast energy effectively scours and compromises the hardening of the tunnel lining and structure deep below. The engineers could not guarantee that the massive shock and debris would not shatter the sensitive internal equipment or fatally compromise the structural integrity of the command center's pressure hull, despite the hydraulic suspension system. This single, critical point of vulnerability transformed the sanctuary into a strategic bullseye. Furthermore, the complexity of missile deployment and fueling within the underground environment added logistical and safety risks that were deemed unacceptable. The ICBMs had to be maintained, fueled, and armed inside the complex, requiring immense volumes of space and introducing the risk of internal accidents. A pre-launch explosion or a fuel leak inside the integrated silo could release toxic propellants or cause a massive conventional explosion that would threaten the life support and structural integrity of the entire underground city. The sheer logistical difficulty of moving massive, multi-stage ICBMs into the deep subterranean facility for maintenance and replacement was a continuous, high-risk operation that added exponentially to the project's operational cost and vulnerability profile. The need to maintain perfect environmental controls within the silo complex to prevent fuel degradation and equipment malfunction added another layer of engineering complexity that was rarely achievable in practice. The strategic debate also centered on the survivability of the communication link after the second strike. Assuming the command post survived the initial strike and successfully launched its retaliatory missiles, the DUCP would then need to communicate with surviving military forces and assess the post-strike damage. This required reliable, hardened communication lines to survive the intense electromagnetic pulse, EMP, and ground shock of a nuclear war. However, hardened cables and antennae links running a mile up to the surface represented easily exploitable pathways for sabotage or secondary attacks. The communications equipment needed to be immensely powerful to penetrate the deep rock, yet it had to be sensitive enough to receive faint signals from distant, damaged surface assets. The trade-off between communication capability and invulnerability was never resolved. The bunker was either perfectly secure but functionally blind, or it was communicative but strategically vulnerable. The sheer technical difficulty of transmitting high-frequency command signals through thousands of feet of solid rock led to the realization that external, vulnerable antennas would be required, completely defeating the purpose of the deep burial. The operational complexity of initiating the retaliatory strike from the depths was another point of failure. The command sequence had to be executed flawlessly under conditions of extreme stress, sensory deprivation, and immense psychological pressure. The sheer time delay involved in confirming the launch order, preparing the missiles, opening the massive surface blast doors, and executing the launch sequence introduced a critical delay. In the age of rapidly advancing Soviet missile technology, every minute counted. The time required for the command to transition from survival mode to offensive launch created a critical window of vulnerability during which a secondary strike could potentially eliminate the entire retaliatory capability. The complexity of the integrated system risked paralyzing the final launch authority under the precise conditions it was designed to survive. The engineers could not guarantee the rapid, flawless sequence required for successful launch under immense internal and external chaos. The financial and strategic absurdity of the DUCP became clear when compared to the rapidly evolving technology of mobile missile deterrence. While Project Zeus demanded the ultimate concentration of assets into a single, fixed, multi-billion-dollar target, the military was simultaneously developing submarine-launched ballistic missiles, SLBMs, and rail-mobile ICBM systems. These mobile platforms offered superior survivability through dispersal and stealth. A submarine submerged in the ocean is practically untargetable, and a missile launched from a rail car, constantly moving across the continental rail network, is extremely difficult to track and eliminate. These mobile options provided a more robust, decentralized, and ultimately cheaper method of guaranteeing the second strike capability, rendering the fixed, subterranean ICBM silos of Project Zeus strategically redundant and economically obsolete before construction could even begin. The strategic brilliance of mobility decisively defeated the brute force engineering of fixed hardening. The sheer cost of Project Zeus was a continuous political target. The initial staggering estimates only accounted for the excavation and construction. They failed to adequately budget for the perpetual operational costs associated with maintaining the complex life support systems, the continuous replacement and modernization of the ICBMs, the security costs, and the eventual multi-billion-dollar decommissioning and cleanup of the massive, potentially contaminated subterranean structure. The political argument against the project was simple. Why build one incredibly expensive, strategically vulnerable bunker when the same investment could field multiple, highly mobile, and stealthy missile systems that offered superior survivability and global reach? The project was defeated by the superior economics and strategy of mobility. The investment was seen as a colossal waste of resources that would only finance a guaranteed failure. The fourth and final phase of the deep underground command post history is the lasting legacy of its abandonment, a decision that fundamentally solidified the military's pivot away from fixed, massive assets toward mobile and dispersed deterrence. The cancellation of Project Zeus was not the end of underground facilities, but it was the definitive end of the concept of the integrated, deep underground nuclear offensive base. The military planners learned that the laws of nuclear physics regarding blast shock and projectile penetration simply cannot be ignored through brute force engineering. The core lesson learned from Project Zeus directly fueled the development of less deep, non-offensive command facilities. Subsequent hardened command posts and continuity of government bunkers were built at far shallower depths, relying on distance and hardened exteriors rather than trying to withstand a direct hit. Critically, none of these subsequent facilities ever incorporated integrated ICBM silos. The failure of Project Zeus proved that the vulnerability introduced by the launch ports was simply too great a price to pay for the marginal benefit of having the commander next to the missile. The subsequent strategy focused on separating command, survivability, from strike, dispersal, relying on remote communication links to launch mobile systems. This separation of command and launch authority ensured that the destruction of one fixed site could not paralyze the entire strategic defense capability. The financial absurdity of Project Zeus established a crucial precedent for defense procurement: the need for rigorous, realistic cost analysis of long-term operational and decommissioning liability. The estimated trillion-dollar system cost of the DUCP forced military budgets to prioritize cost-effectiveness and redundancy. The money saved by canceling the DUCP was channeled into the massive expansion of the Navy's submarine fleet and the solid-fuel Minuteman ICBM program, both of which offered vastly superior survivability per dollar invested. The DUCP became the quintessential example of a technological ambition that failed because its price tag exceeded the strategic utility it provided, serving as a permanent warning against the pursuit of absolute, high-cost invulnerability. The final strategic decision was simple arithmetic. It was exponentially cheaper to hide the weapons than to shield the command. The environmental and logistical challenges posed by the project's massive deep excavation also left a lasting mark on civil engineering. The problems encountered in simulating deep rock, spalling, and microfracturing pushed the boundaries of rock mechanics and large-scale TBM development. While the project was canceled, the advanced research into deep drilling and shock absorption benefited subsequent, less ambitious civil engineering projects, such as deep scientific research facilities and large-scale underground energy storage caverns. The DUCP failed as a bunker, but its research contributed essential knowledge to the science of subterranean construction, proving that even a failed megaproject can yield valuable technical insights. The data collected on deep rock stress fields provided invaluable information for designing stable, long-term geological repositories, ironically helping to manage the nuclear waste problems created by other projects. The political sensitivity surrounding the project's secrecy and the immense concentration of power within a single, isolated complex also influenced future defense planning. The fear of a single, decapitating strike eliminating the entire command structure and retaliatory capability led to the development of highly dispersed command and control systems, including the use of airborne command posts and decentralized communication networks. The project's failure reinforced the wisdom of decentralized leadership and strategic redundancy, ensuring that the survival of a nation's deterrent capability was never reliant upon the integrity of one immovable concrete shell buried a mile deep. The strategic importance of the Looking Glass airborne command post and the development of hardened, mobile communication vans were direct descendants of the lessons learned from the DUCP's fixed-target vulnerability. Project Zeus remains a chilling conceptual monument to the Cold War's pursuit of absolute survival and power. It was a project that tried to cheat the laws of physics and nuclear warfare simultaneously, only to be defeated by the simple, unyielding fact that a launch port is a vulnerability and a mile of rock cannot perfectly shield against the combined forces of blast shock, channelized debris, and the financial gravity of $1 trillion price tag. The dream of the impregnable subterranean city was defeated by the superior strategy of mobile warfare and the ultimate economic law of diminishing returns. The command post was too big to build, too rigid to survive, and too visible to be viable. The ultimate fate of Project Zeus lies in the archives, a testament to the fact that when technology meets the existential threat of nuclear war, the solution is almost never found in brute force construction, but in the intelligent deployment of mobility and dispersal. The project was not a technical impossibility. It was a strategic and financial absurdity. The decision to cancel the DUCP was the definitive moment the military realized that the money should be spent on making the targets impossible to find, not impossible to kill. The final question remains: Project Zeus failed because a fixed ICBM silo on the surface compromised the underground facility. Today, hypersonic maneuvering warheads make any fixed target vulnerable. Do you believe that modern breakthroughs in deep rock tunneling and material science could ever guarantee the survival of a fixed underground military complex? Or has the speed and accuracy of modern missiles made any permanent land-based bunker concept strategically obsolete forever? Join the discussion below and tell us, what is the single biggest security flaw in the concept of a bunker that must also launch rockets? If you enjoyed this professional deep dive into the abandoned engineering of the deep underground command post, like this video and subscribe to the channel for more stories about the incredible projects that were never built.